Are we calling this like kind of how to read studies, or is it specifically about the...
This is just a statistical critique of this study because I thought it warranted some, and it's been getting a lot of, social media buzz and stuff, and
Oh, really?
Yeah. If you're in that sort of, group kind of thing where that's in your algorithm.
Okay.
Yeah.
So the premise is you saw this study being touted,
Mm-hmm.
and you went and checked it out.
Yeah, on both sides too, like people pro the study and people against the study.
Okay.
Yeah.
And something about it annoyed you. That much I know.
Yeah, we'll say that, yeah.
And then you sent it to me to just check out.
True, but I want to be clear that I'm critiquing primarily the statistical methods in the study.
Okay.
I'm not critiquing like their whole background in developing this kind of study and why they did it and all of that stuff. And it's mostly just on the statistics as much as possible.
So I checked it out.
Mm-hmm.
It's something that I have very little knowledge about. Cholesterol, and
yeah,
I do use like AI to help me with research, and in this case I used it more than I normally would because like some of it I'm not even familiar with the terminology.
Yeah, it does take a lot of background knowledge to kind of assess it in an informed way.
Yeah.
And I'm gonna try to keep that to a minimum, just enough to like understand what I'm talking about.
Okay.
Because that could take like hours and hours of
right. It's I'm guessing it's a pretty deep topic. It's not
for sure. Yeah.
Okay, so maybe we should say what the study was.
Yeah.
So it was basically they got a bunch of people who were on a ketogenic diet, and they measured whether there was a plaque buildup over a year, and found that they concluded that there wasn't, that ketogenic was a fine diet to have in this aspect.
That's not exactly what they concluded.
What did they say?
Let me share my screen.
Yeah. Do you have a presentation?
Do I have a presentation? No, this isn't the presentation. This is the actual paper.
I know. I recognize it.
Yeah. So just to be clear, we're talking about the latest study that's come out. I think it was a little over a month ago, and the title is called Plaque Begets Plaque, ApoB Does Not, longitudinal data from the KETO-CTA trial.
Right.
So yeah, of course I made a presentation, and this whole presentation will be available in the link in the description. I'm doing it right.
Yeah.
So my presentation is titled Plaque Begets Plaque, ApoB Does Not, the statistics cause doubt.
Okay.
So I do have a quick summary of the study, just so we know.
Okay.
And then maybe we'll, after this summary, tell me if that was what you understood. So like you were saying, it's a 1-year prospective cohort study. So not a randomized controlled trial. They just got this group of people, followed them for a year, and took like plaque scores at the beginning and at the end. So what we call like a baseline, and then 1 year later, a follow-up. And in the study, they have multiple metrics for this plaque score, but they seem to focus on one called NCPV, which is non-calcified plaque volume. And that's like the main outcome variable they look at. And that's what all their conclusions are based on in the study. Mm-hmm. And the one, I guess, important thing about this study is that it's on this kind of unique subgroup of people that they call lean mass hyperresponders, which they came up with this term some years ago and have been, developing this idea for a while. But it basically means that you've been on a ketogenic diet for at least 2 years, and you're lean, you're healthy in every aspect metabolically. You don't have any like diseases or anything, but the only thing that looks potentially unhealthy is that you have high LDL-C cholesterol and high ApoB. So it's kind of like this, you're healthy, but you have these things that might be a marker of heart disease developing later.
I've never heard ApoB.
I know it's I know. So yeah, just ApoB is like a kind of a different kind of way to think of it as like a more specific LDL-C.
Okay.
Like, don't get too deep into this now. I don't want to, like, it's this whole thing, but it's just a different kind of like cholesterol, like probably more specific, and most likely the research says that it's even more associated with heart disease than LDL-C.
Okay.
So that's the participants, followed over a year, plaque score at the beginning, at the end. Mm-hmm. And their conclusions actually were that there was no association between ApoB or LDL cholesterol and plaque progression. And the predictors also, they did find that baseline plaque was a predictor for the change in the plaque volume at the end.
Right.
So that's that delta NCPV is what is change in that.
Okay.
We'll go into this a bit more, but just setting up.
Right.
And then just about how they modeled that is they just use these kind of models, which we'll explain later what they are. And their big conclusion, which they entitled the paper, Plaque Begets Plaque, ApoB Does Not.
Right. So they found that ApoB does not associate with the plaque buildup. Mm-hmm. But if you already had some plaque, mm-hmm. you're likely that it will grow.
Mm-hmm. You're likely to have more plaque in a year.
Right.
Yeah.
So yeah, I got that far. And when I was looking for things that would be problematic with this, I guess the most obvious thing was that there was no control group.
That is a good point. And that means it's really difficult to say it's causal.
And the other thing is, and this is where AI was a bit of a help, that it might be too short of to determine, because plaque can build up over decades. Mm-hmm. And a year, I don't know if it's decades, but a year seems to be way too short of a... Mm-hmm. Hearing it from you, it also occurs to me that the way they selected these people isn't, they just got a bunch of people who were already eating a certain diet and were probably health conscious.
For sure. Yeah.
Um,
I think I know where you're going, but they identified this group of people, and they basically want to know more about them and figure out if you have these markers that you're otherwise healthy, except your cholesterol's high and ApoB's high, that maybe you won't develop heart disease, you won't develop plaque, or there'll be some other reason that you would develop heart disease. I guess they were unsure if the cholesterol ApoB causation of heart disease would also play out in this unique group.
Why did they? Well, not why did they, but ideally, there would also be people who didn't follow the ketogenic diet after the study started.
Yeah, well, basically, I think that comes down to funding. They just, they can only do so much with the funds they get. They actually, one interesting thing about this study is that it was crowd funded. It wasn't like a university funding it or a company funding it. Like, they actually had social media presence. People donated to provide funding for the study and run it. So
I didn't know this was a thing.
I don't think it has been. I'm not sure if this is like the first study to do it, but it's very interesting. Like, it's pretty cool that they could do that. I really
yeah.
I mean,
but the thing that's raising my eyebrow now is, like, if it was, since we recently talked about the meat carnivore crowd, like, if they funded a study.
I I know where you're going. Yeah.
It's like the documentary of flat earthers.
It's not that bad.
No, it's not that bad, but
no, I know what you're saying. That, like, when we analyze studies and we see, it's the Egg Council that provided funding for this study that says eggs are good, then it's often people are like, it's got to be biased. So I see where you're going, but it doesn't necessarily mean anything.
Sure.
Do you have any more thoughts on, like, I don't know, the general quality of the findings or anything? Like, were you convinced?
Well, I didn't look at the numbers. I didn't know your issue with it was with the numbers. I thought it was more of the setup of the experiment.
Mm-hmm. Like, it was poorly set up and
something
too many
like
problems.
that.
Yeah. Okay. I got you. I'm not saying there aren't any problems with it. I just want to focus on the statistics in this.
Yeah.
Because I think it'll be an interesting analysis, let's say.
Okay.
You ready?
I hope it's not as bad as the using total population count.
Oh, the total, instead of the percent or the ratio. There are some interesting issues with it, I'll say.
Okay.
And they will become, and some are more obvious than others. Some take a bit of math to figure out why. I've tried to add some visualizations that will explain it, I think, in an easier way. And I've kind of divided this presentation into like a main presentation, and then I'll summarize it at the end, but then I will also have some additional things to talk about that like didn't fit the main part.
Okay.
All right. Let's go. Okay. So the main sections that I'll talk about are first the change in the NCPV, the non-calcified plaque volume, as the outcome variable, so the choice of that. And then their modeling choice, which they base their conclusions on, which is univariable linear models. And then we're going to talk, I'm sorry, but we're going to talk about some Bayesian inference. I'll do a quick intro to that. Don't worry about it. We'll just go through it. I'll talk about their Bayesian prior choice. And then I'll talk about their interpretation of the results of this Bayesian analysis. Mm-hmm. And then I'll do those additional concerns at the end. Are you already overwhelmed?
I'm just wondering if there are more than 4 people on the planet who would...
Yeah, maybe a bit more, but...
Okay.
But I think at least the first 2... I think people who don't understand statistics, I think will still understand what I'm trying to explain.
Yeah.
Yeah, this will be interesting. Okay, so let's go. All right. Okay, change in NCPV as outcome variable. So they said plaque begets plaque. And I'm saying, is that a mathematical artifact and clinically uninformative? Well, let's look at that. Mm-hmm. Okay, and any quote I have that's like blocked off on the side, this is a direct quote from the study. Yeah. And I'll just note that. So they said that all baseline plaque metrics, that's coronary artery calcium, NCPV, total plaque score, and percent atheroma volume, were strongly associated with the change in NCPV. So we got change in NCPV as the outcome. Got it?
Yeah.
Okay. Now, just got this quote from a professor of biostatistics here. Many authors and pharmaceutical clinical trialists make the mistake of analyzing change from baseline instead of making the raw follow-up measurements the primary outcomes, covariate adjusted for the baseline. So they basically are doing what he says is a mistake. And I'm going to explain some reasons why it's considered a mistake by...
Oh, this isn't a quote by them. Okay, no. Got it.
This is a quote by...
Yeah.
Sorry. Yeah. This quote in the kind of orange is a different, not related to this study. A professor of biostatistics just at a university. Okay. So just to be clear, the change in non-calcified plaque volume is the outcome in this study. And that's simply, you get the follow-up minus the baseline. Simple, mm-hmm. Just want to be clear. And this is just a way to write a linear regression model, simply. So you have the outcome variable here. The input, for example, is that means it's at the baseline with the 0 and CPV 0. Don't worry too much about these other terms. It's just error and like the intercept.
Okay.
This beta is that coefficient that we look at. It's the slope in the charts that you see when they fit a line to the data. Make sense?
Yeah, I think so.
Okay. So I'm going to explain why this choice, this making change the outcome, can obscure clinically meaningful patterns, inflate the regression error, and reducing the model precision, and introduces a concept called mathematical coupling.
All right.
All right. So let's talk about change scores obscuring clinically meaningful patterns. So this is not the actual data. I want to be clear. I don't have the actual data. This is just an example of what you would see possibly from the data set. So you have each row is the subject, like a person, ABC.
Since the issue is primarily with their calculation, we don't need the actual data. You just are using this to demonstrate where the problem could be.
Yeah, theoretically.
Okay. Yeah.
So you have 3 subjects. You have their ApoB, and you have their change in NCPV. So you notice that the change in NCPV for each of them is 20. Same change. But their ApoB is very different.
Yeah.
Right? Now, what would you conclude just off these three?
I would just say it didn't matter.
ApoB.
Yeah.
On the outcome.
Correct.
And that's definitely what this appears to show. No doubt.
Right.
The problem is, what if we actually look at the values of the baseline and the follow-up? So now I've added NCPV 0 and NCPV 1, which are baseline and follow-up.
I see.
Does something look a bit different?
Yeah. One of them doubled.
Well, they're all different by 20.
Yeah, but one of them doubled.
One of them doubles, one of them, well, they all, so the scale is different. But also look at the numbers compared to the ApoB.
I'm not sure what you're getting
So do you see how ApoB goes up for each subject?
Yeah, and the NCPV goes up a lot with it.
Right. But the change in NCPV does not.
Right.
And they're saying that ApoB is not associated with the outcome variable, which they define as change in NCPV. So, okay, maybe that might be true, but that doesn't mean that ApoB is not associated with plaque.
Got it.
Do you kind of see how I'm showing that with?
Yes.
You can have the change be the same, and it looks like there's absolutely no correlation, no association between those two variables.
Without knowing what the actual values were before and after.
Right.
Yeah.
And that is the problem. One of the problems basically with using this.
Now that you say it, I'm like, why would they do this? You know what's interesting? When you show me the first numbers, I'm like, okay, but because they don't start with this, they start with the raw data.
They start with the design of the experiment.
Yeah, like why would they go for that?
There's a few reasons, and I think one is that it has been done in the literature. That is definitely out there. And the problem with that is that they probably didn't have statisticians developing the design of the experiment or the statistical design. And the other problem is that on the face of it, it does make sense a bit. Like you're like, I want to know what changed, how much calcium, how much plaque changed.
Yeah.
So this is just a summary of what we've just talked about, that all three subjects had the same plaque progression. So the same change, but they started and ended at different levels, and ApoB increased, but the change doesn't reflect that. And if you model just the change on ApoB, you get like no slope, no association. But it's clear that ApoB tracks with the absolute number of, absolute plaque.
But by this logic, they didn't even need to wait a year.
Having the year, they kind of wanted to see how plaque would develop. I know what you're saying, that you could just make an association at one time point. That is true. You can. But with having 2 time points, you can have some more precise analysis because you're tracking people's growth in the plaque over time. But
it would make more sense if some people changed their diet, but since
that's just not what they were concerned with in this study.
Okay, I got it.
Okay. This is a bit more of a statistical issue with this, choosing the outcome as the change. And this problem is that when you do that, you kind of combine any measurement error from the baseline and follow-up, and that inflates the model residual variance. So any model that you fit to the data is going to have errors or residuals that are just left over that you couldn't explain by the model.
Mm-hmm.
And if you model the change, you're kind of adding that error from both of those measurements. I know it makes a bit. This will have a visualization. So, okay. So, and this is simulated data, of course. I tried to use the summary stats in the actual study. So maybe it's somewhat close. I don't know, but so I'm looking at comparing two models: the change in NCPV, if that's associated with ApoB, and then the other model, which is the follow-up NCPV modeled by NCPV at baseline and ApoB.
To be clear, this is one of them is what they did.
They did,
and one of them is what you would recommend them doing instead.
Yeah. Well, pretty much. So yeah, they modeled the first one. That was their model. But this is not their exact model. This is, of course, the simulated data.
Yeah.
So you can see this is the residual standard error, and you can see it's almost over twice as high in this model on the change score. And the p-value for ApoB is well over 0.05. R squared is almost nothing. So that indicates, like we were talking about before, the ApoB on the change doesn't have any association. However, on that data, if you model the follow-up NCPV by the baseline and ApoB, you will actually get a p-value well below 0.05. You will get an R squared very high, which is probably, this is definitely fake a bit, and the standard error is a lot lower.
How do I know? Just to critique you.
Yeah, for sure.
How do I know you didn't just make up some numbers that will come up with these results?
Well, anybody can look at the code I made for these.
No, but
you mean the p-values and stuff?
No, like the inputs that resulted in these numbers.
Oh, the simulated data.
Yeah.
All I can say is that I simulated random numbers from a normal distribution based on their summary stats, which is something you can do in programming. And it's not going to be exactly the same as the real data, for sure.
But the summary stats are what they got.
What they got, yes.
Oh, okay.
The data is not exactly the same as what is in the study.
Yeah. I got it.
And I put in a kind of weak artificial association with ApoB.
Okay.
So all I'm saying is, if there's an association with ApoB that should be in there, you won't pick it up with this change score model.
Got it.
Okay. And this chart is just a distribution of the residuals or the errors from both of these models. And you can see that in the change score, that's the delta NCPV. That's the kind of orangish one. The error is much wider. That means the errors are much larger. The model's not that good. So remember, this is like the same data set. It's just what you chose to model from the data set.
Yeah.
Okay. I know it's a bit of a weird concept, but
out of curiosity, did they not show the data?
That gets into more of the not statistical part of the critique, but no, we don't have the raw data.
Okay.
That would be really cool. I wish they did. They might later. I think I heard they might later
Okay.
allow people to get it, but we only have some summary statistics from the data, like mean and standard deviation and things like that.
Okay.
All right. Okay. This is the section about mathematical coupling. And I'll just remind you that in one of their models, they modeled the change in NCPV directly on its baseline value. So they said, does the baseline value predict the change?
Mm-hmm.
And they concluded, one of their conclusions was, it is highly associated with the change.
Yeah. Does
this setup sound a bit strange somehow? I don't know.
Well, yes.
Okay. I'm going to explain why it sounds strange mathematically. You have an intuition that something is a bit off.
I have an intuition that when a number is a certain value, if you measure that value down the line, like, of course it's going to be affected by where you started.
Mm-hmm.
That's my intuition.
That's yeah. You should have been a statistician.
Yeah.
Okay. This introduces mathematical coupling because NCPV 0 now appears on both sides of the equation. So all I did was take this change score and break it out into what it is. It's just follow up minus baseline. And that equals this other term, which is the baseline plus the beta, and the error and the intercept. But I think even if you don't understand, what the terms mean here, you can see that something feels a bit off. Feels a bit not what it should be. And this kind of idea, this concept is called mathematical coupling. And just I wanted to get a quote because it's just show that it's an actual thing in the literature, in the statistical literature. And just to read it, mathematical coupling occurs when one variable directly or indirectly contains the whole or part of another, and the two variables are then analyzed using correlation or regression. As a result, the statistical procedure of testing the null hypothesis that the coefficient of correlation or the slope of regression is 0 or not associated might no longer be appropriate.
Mm-hmm.
And that no longer be appropriate is kind of, scientific studies speak for, you don't want to do this. It's not a good idea.
Trash.
Something like that. Okay. So this will be the math part.
Okay.
Yeah, so just what they kind of laid this out in their thing, and I just put in our terminology in it. So just to explain quickly, this is the regression part where the main thing to look at is the beta, which is the slope of the line, right?
Mm-hmm.
Okay, and within that beta, to calculate that, you have to get the covariance of these of the two terms and divide it by the variance of your baseline. But the problem is that you have this covariance that is actually that minus the other one, the baseline, the follow-up minus the other one. And you do some rearranging, blah, 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 blah. And eventually you get this equation that's simplified, and you see this -1 at the end of it. And this equation is just the correlation between the NCPV 0 and 1, and then the standard deviations divided by each other. So this rho, that's the Greek letter, is the correlation between those two variables. multiplied by their standard deviations, and you have to subtract the 1. Don't worry too much about the details.
I wasn't.
Okay. So this -1 at the end, which you get to, that means that basically the slope is going to be generally pushed negative to a negative, where, like, say these things didn't correlate, then you would have a value that's lower than 1 on the left of this, and you would subtract 1, so then it becomes negative slope.
Mm-hmm.
The interesting thing is that in their results, they got a positive slope, which actually can happen, but then things become a bit even more messy, where just to say that this is clearly not a clean estimate of the actual slope. It's like there's some mathematical issues in there.
Mm-hmm.
Yeah, and then this one is just saying the slope will be greater than 0 if the correlation is greater than the outcome of this division, the 2 standard deviations. But basically, the mathematical coupling pushes the beta down by 1. And a positive beta is only possible when that term is greater than 1. And you can satisfy that inequality, that greater than 1, if the standard deviation of the follow-up is higher than the baseline, or if the measurement reliability is not as good in that and the error is higher. So just saying that a positive slope doesn't mean it's actually positive. It can have this coupling issue in there. So in this study, it looks like that might have happened.
Yeah.
That the follow-up standard deviation was higher than the baseline. I don't know. Yeah. We don't have those statistics. And this is just kind of restating it, that you just have that mathematical artifact in the beta, the slope, and you can't just add 1 and that will fix it. Like, it's more complicated than that.
I just wanted to kind of repeat what you said,
mm-hmm.
as I understood it, just to make sure that we're on the same page. I got the part where them using a number, like a variable in the calculation, and how that could be problematic.
The change modeled by the baseline, yeah. Mm-hmm.
And I got that it will be offset by -1.
Mm-hmm.
And then the stuff that you said after that.
Yeah.
No. I'm serious. And so that in this case, they got a +1.
Mm-hmm.
Was that because you kind of see somebody in defense of the way they did it to come and say that, but no, we got a positive result there? And then that's why you explain that it can happen that this results in a positive, and it doesn't mean that it's better or whatever.
Yeah, it doesn't mean it's all okay and that it's not a problem. Yes, that is why I had to go.
Or like,
that's why I had to go.
Even though there's -1, we still got a positive thing, which means like it's super positive or something like that.
It's at least more than 1.
Work like that.
Mathematically,
okay.
Yeah.
Okay. Continue.
Okay. So what I've done, this is not the data, this is just random data, just to visualize the more simple version. So not that the beta is greater than 1, just the simple one. Okay. So this is some R code. And basically I've got the number of values to generate. That's the N. And I have a normal distribution, just pulling random values from a normal distribution that has a mean of 100 and standard deviation of 10. So they're kind of centered around 100, standard deviation of 10. That's what I'm calling baseline. And I have the same thing, except for the follow-up, it's a mean of 120. So just the center is at 120. Does that make sense?
Yeah, the distribution is the same, but it's just moved 20 points.
And it's just pulling random values from there.
Yeah.
Okay. So the baseline is just a column of 100 numbers.
Mm-hmm.
And the follow-up is a column of 100 numbers. Right. And the mean of each of those is about 100 and 120. Okay. And this delta is the change, which is just the follow-up minus the baseline. So just subtracting each of those numbers, like if you think of it in a row, like this minus that. Okay. Make sense?
Yep.
And these are randomly generated. So should there...
I don't know why you picked 120, but other than that, it makes sense.
It was just, I had to pick something, and I wanted to pick something different that would just show a different number.
Okay, but the results would have been the same if you had picked 80?
Yeah. Mm-hmm.
Okay.
Yeah. Similar. They'd be similar. Okay, so you would agree that baseline and follow-up shouldn't be associated, correct? Like if I plot them on a graph, which is what I'm going to show you. Okay. So this is baseline on X axis. This is follow-up on Y axis. It's clearly you can see there's no relationship. Agree?
Yes.
Our beta is very small. Our p-value is large.
Yeah.
Make sense?
Yeah. These are randomly generated, right?
Yes.
I guess my mind's going there. Yes.
Yeah.
Makes sense.
Okay. Now what I'm going to show you is the same thing, but I'm going to show you the baseline and the delta, the change. The change will be on the y-axis. Okay. And I'm going to show you the beta and the line.
Mm-hmm.
Can you guess what's going to happen?
I'm at the edge of my seat.
So we got...
Okay, hold on. Let me see. Why did we get this result, though?
I know, isn't that... It is kind of... It's like, what? Why?
Yeah.
But that's the mathematical coupling idea. That it's not a real association. It's just due to that mathematical property.
Oh, yes. Okay, I get it.
It is a weird concept, I know.
Is it though? Because if you think about it,
when I say real, you can interpret that how you like. Like,
can you tell me if I'm getting this right?
Mm-hmm.
Like, I'm just wondering why we got these results, and it's because.
Do you want to look at the math? It's that -1.
No, I don't want to look at the math. I want to because we generated the numbers randomly around 100. Okay, and if let's say one of them was 110 or 115, there's only so far they can go from there in the second number generation.
Mm-hmm.
Like, it's more likely that they will move less because they're more likely to be around the mean in a normal distribution.
Are you talking about the difference or the...
Yeah. You generated the numbers around 100.
Mm-hmm.
And then you generated them again around 120.
Mm-hmm.
It's obvious why it would be like that.
Is it obvious why this is a mathematical artifact and not like indicative of biology or something?
Yes.
Okay. That's the idea I'm trying to get across.
Yes. It's like
Like the baseline, of course it's associated with that. It's within it.
yeah.
Yeah. Literally.
Exactly. I'm trying to come up with a different example.
I know, yeah.
Just to but
it's interesting. I think it's really it's less obvious than you'd think. Like even when I was like creating this, I was like, is that really going to work? Is that really going to show? Yeah. But, okay. I think we got this.
Yeah. I think so too.
Okay. I'll just quickly talk about the alternative that we kind of already touched on, which is just modeling the follow-up, but kind of controlling for the baseline. And that makes it at least you avoid that mathematical coupling problem where, you reduce the error and you have the controlled by the baseline. So you can see that it's more clinically meaningful, like in our first part of that. This just stat stuff. It's like, this is kind of like an ANCOVA analysis covariance style model, where you're just controlling for this baseline. It's not exactly ANCOVA. There aren't, never mind. It's just, it's more usually made for group, but it's basically like controlling for a variable in there.
Okay.
That would be the recommended way to do it. That I think most statisticians would agree with. This is just to summarize: a slope from change in delta modeled by baseline change in NCPV modeled by the baseline may reflect math and not biology, because the outcome is built from the predictor. And using the change scores also compounds the error and weakens the model precision. Just like we said, to isolate the real effects and preserve clinical meaning, we should follow up. We should model the follow-up directly and adjust for the baseline. I just have a few quotes just to kind of emphasize that it's not like a secret, like unknown thing. Like it's definitely in the literature that you shouldn't do this.
Okay.
But there are still many studies that do it. It's not just this one. I want to be clear. Like
I imagine there must be, because it seems to be a thing that's come up multiple times.
It definitely has. So, like I said before, Plaque Begets Plaque. Is it a mathematical artifact? Maybe. Is it clinically uninformative? So
okay. Well, now that question makes more sense.
Yeah. Good. Okay. That's just some more references if you want them. If you want to read some reading. All right, that's part one. Okay. Now let's talk about univariable linear models. The way they modeled their associations. And I'm saying at best these are hypothesis generating exploratory type models, and at worst they're misread as proof. Okay, so direct quote from the study: linear models on the primary NCPV and secondary outcomes were univariable. Now, what does that mean? That means only one variable is in the predictor or independent variables. There's only one independent variable, one predictor variable for the outcome. But they did collect multiple predictors in the data that they have. They have age, sex, ApoB, BMI, triglycerides, many other things that they could have included in the model. For some reason, instead, they modeled and reported only on the univariable models in their conclusions. And I just want to, like, this is clear omitted variable bias, which is just the terminology for, omitting the other predictors that might explain the outcome in a better way. And this means that a predictor may appear significant in a univariable model, but its effect could vanish once relevant covariates are included.
Is this like the confounding?
It's very similar to that, yeah.
Okay.
Yeah, exact same idea.
If I want to push back, if they had measured all these other variables like age, sex, ApoB, BMI, etc., wouldn't that increase the chance that just by sheer luck, one of those things would have a really high predictor and high low p-value? And
you're talking about the multiple testing problems?
Yeah.
So, but with this model, I'm saying you would put all of these in one model. And that kind of avoids that because you're just doing it in one model. And you can see with just this one model what is the, significant predictors. The way they're doing it, they definitely could have modeled all of these variables independently, like separately is that what you're saying, like in a separate univariable model?
Yeah, I guess when you say put all of that in a model, in my mind, I'm having difficulty grasping how that's different than just checking how each of these separately correlates with the outcome.
Okay, so if you check them separately, you will just get, does this variable correlate with this variable? But that doesn't check if there was actually another variable that was more important or reduces the effect of that one variable. Like if you hold one variable constant and the other variable is the one that is making the outcome, more predictive.
Okay, got it. But just before we move on, when you say put them in the model, what does that entail?
So like put more variables in one model?
I mean, like functionally.
Okay.
Is it a code, a program? Is there a formula? Is it a...
So they modeled, this is what they did. They modeled the change in NCPV by ApoB. That is a univariable model, just one predictor. And then they would look at this beta and the p-value associated with that beta, and is it significant or not? In their modeling, it was not. Now, what happens if age is in there? Because all these people are a different age.
Yep.
There is there's a range. There's a small range. I think it's like 15 years, maybe 10 years, but it's definitely a range. It's not like, it's not the same. They don't all have the same age. If they put age in the model, you can basically say, if we hold age constant, how much does ApoB affect the change in NCPV? And the other way around too, if you hold ApoB constant, how much does age affect NCPV? So it's kind of, you get separate betas, and those are representative of only the impact, of the impact of ApoB controlled for age, and vice versa. Does that make sense? How this top model could be biased one way or the other, really. Like if you see a significant association here with ApoB, adding another variable can remove that significant effect. Or vice versa, if you don't see a significant effect of ApoB, adding a variable can make ApoB's effect actually appear significant later.
Sure. Yes.
Right. Both ways is what I'm saying. Okay. So just, summarizing that, univariable linear models make omitted variable bias likely confounding almost certain. It's just, there's, I don't think anybody can look at this univariable model and say nothing else could have an effect on NCPV that's also not correlated with ApoB. Like
they gathered all this extra information and then didn't take it into account.
Not in the reporting of the conclusions. Not in this study. No. Okay,
seems strange.
A little. Yeah. Okay. This is just a quick aside that they did. This is a quote from the study. Estimated lifetime LDLC exposure was only a significant predictor of final NCPV in the univariable analysis, but lost significance when age was included as a covariate. Both age and lifetime LDLC exposure lost significance when baseline CAC was included in the model. So the strange thing about this is that, and they also have one more of these multivariable models. They clearly ran some multivariable models, but for some reason, all the conclusions that they reported were only based on the univariable models. Plus, they only reported these three multivariable models in the study when there's clearly, it's not hard to run these multivariable models. Like you just, it's just a few letters that you add in the code. I don't know why they didn't do that. I don't know. But it's a bit.
Okay.
Yeah, this is just a quote from their abstract. So like the whole, summary of the whole study. It says neither change in ApoB, baseline ApoB, nor total LDL exposure were associated with the change in non-calcified plaque volume, that NCPV or TPS. All baseline plaque metrics, coronary artery calcium, NCPV, total plaque score, and percent atheroma were strongly associated with the change in NCPV. All these statements are based on these univariable models. Just one model, one variable predicting the outcome, not adjusted. And this is definitely overinterpreting the results from limited models. Like,
okay,
it's fine to run these models, like these univariable models. There's no problem with that. But that's like the first step in the modeling process. Like you wouldn't have that as the final conclusion of your paper.
It's stop there, I guess.
Yeah, it's strange to say the least.
Okay.
I don't know if I don't know. I've done a lot of modeling, of course, in data sets, and like I would never present that to the client as like, this is my final conclusion based on this model, when there's other variables in the data set.
I can, like, if you were hired to conduct this and then you had all this data and you didn't somehow adjust for age and just presented it like, I can see how that's incomplete, shall we say.
Yeah, definitely incomplete. Definitely, yeah. Are you ready for Bayesian modeling?
Bring it.
All right, let's go. All right. So I'm going to say the Bayesian modeling that they did is unusual, fragile, and overstated.
Wait. What is Bayesian modeling?
Okay. So this is going to be a very superficial summary of the difference between frequentist and Bayesian statistics. And I'm just going to focus more on what we can interpret from the outcome of these different statistical methodologies, rather than like explaining all the whole philosophy behind each one. It would take a lot to explain that. But when we say frequentist, that's the normal statistics you're used to seeing, like with the p-values and confidence intervals, things like that. So most of it that you see out there in studies is this frequentist type of statistics. Bayesian is just a whole different philosophy on how you model things, how you actually define probabilities and things. But this is kind of a summary of what you can say in frequentist modeling. You basically, you know the p-value, like the significance. Like if it's over 0.05, it's not significant. If it's under 0.05, it is significant. And you can say if the p-value is over 0.05, like you can say something like, we did not find sufficient evidence to reject the hypothesis that ApoB has no association with the change in NCPV. You can't say that ApoB has no association with change in NCPV.
Sure.
You can never say that directly. It's just something that the way the structure is set up, you can't prove a positive result, or you can't prove a null result. Like it's.
Okay.
I know it sounds a bit weird. This can take a while to get.
No, this is like I think this is pretty consistent with stuff I've read.
Yeah.
I'm just wondering how the next one will differ.
Right. So in the Bayesian philosophy, you're kind of seeing, does data fit the model? And in frequentist, very loosely, you're like, does the model fit the data? Very loosely. So I know that sounds like no difference, but with Bayesian modeling, that actually eventually, if you have everything set up properly and state all your priors and things like that, you actually can say something like, it is more probable that the null hypothesis is true. It is more probable that there is no association than there is. And here is just, there's something called a Bayes factor, which is very loosely similar to the p-value. It kind of is the result of a Bayesian modeling, and the numbers of the Bayes factor correspond to like strong evidence or weak evidence, or things like that.
Question.
Yeah.
Is one better than the other, or just different?
Just different. I mean, many people will argue that Bayesian is better, but Bayesian has lots of problems. It's not. It is not easy. It's a lot more complicated to set up things. And one clear problem that I'll show later is you need a Bayesian prior, and that's always like a issue of how do you figure out the prior distribution.
So why are you advocating for it here?
I'm not advocating for it. I'm just trying to explain, that there are two different statistical methodologies. But just to summarize, in the end, a frequentist can say there's no evidence of effect, and a Bayesian can say there's evidence for no effect.
Can it say there's evidence for effect?
A Bayesian, yes. Yeah, they could also say there's evidence for an effect. But a frequentist could not say that.
Okay.
Okay. Kind of got it.
Kind of got it.
That's enough. Okay, so direct quote from the study. Since lack of statistical significance, p-value over 0.5, should not be interpreted as evidence in favor of the null, like we were talking about, but simply a failure to reject the null, the addition of Bayesian inference adds credence to the finding that there is no association between NCPV versus LDLC or ApoB. Okay?
Mm-hmm.
All right. So basically they're changing into a whole different statistical methodology so that they can support their finding that ApoB has no association with plaque progression, so that they can say it's likely that ApoB has no association with ApoB. That they don't have to say we didn't detect an effect, you know. Okay.
Yeah.
And I'm gonna argue that that's a bit strange and unusual to do in a non-randomized, uncontrolled 1-year observational study on a small, highly, restricted sample, because first of all, the study design is not like a randomized controlled trial. It's not suited to make these strong conclusions about any presence or absence of associations, regardless of how well they model things. Now, if they'd started in the beginning and said, we're setting this whole thing up as a Bayesian experiment, that's legitimate, but it really seemed like after the fact they were like, hey, we could do this. And it'll show some stuff. And also, all of these models are still, they're univariable.
Why is that an issue? Like, if the numbers add up.
Right. I'll try to spell it out.
Okay.
All of these Bayesian models that they're using are still the univariable, unadjusted models that we were talking about before. That could have all of those association, confounding issues. And it's also on that ΔNCPV outcome, which is problematic anyway. And they just want to use, it seems like they chose to use Bayesian inference so that they can imply that there is an absence of effect rather than not just lack of evidence. It's limited modeling and context, and then they will now present this Bayes factor result as confirming their previous modeling, which is just I don't know, it's a strange step to do. That's kind of an opinion, but I think it.
You're allowed to have opinions.
Yeah, I'm trying to be like neutral. I'm just statistical. Like, I wish they had explained more why they chose this.
Okay.
Instead of just, it basically sounds like they chose it just so they can say this thing that there's absence of effect. That's not good enough.
Yeah.
Like, you need some more reason. And this is kind of the whole thing that I'm saying. They're applying a confirmatory leaning statistical framework to a more exploratory analysis that lacks adequate adjustment or robustness. So like the basis, the structure is fragile. It's like the stupid analogy, but like you build a house and it's got a crappy foundation, and you put a small you build a small house on top of it, and and then you like, let's put a second story floor and make it beautiful, and like that doesn't make the foundation better. It just makes it appear like it's a nicer place.
Right.
And this is not to say that Bayesian methods are invalid. They're really cool, and you can do a lot of interesting stuff with them. But it seems like they're just using it to amplify the certainty and create this unwarranted confidence in an analysis that's like structurally weak. It lacks adjustment, it lacks the control, it's not a randomized controlled trial, and the whole design is not suitable for these strong claims.
Okay. I think that makes sense.
Okay, cool. Now we get to talk about Bayesian priors and the choice. So this quote, direct from
the moment we've all been waiting for.
I know. This quote, direct from their study. Bayes factors were calculated using Bayes factor regression BF. It's an R package. And an R-scale value of 0.8 to contrast a moderately informative prior with a conservative distribution width to allow for potential large effect sizes due to the well-documented association between ApoB changes and coronary plaque changes. Okay. What does that mean? Okay, so just in very brief, the Bayesian, in the Bayesian method, you have to determine a prior, and that represents your beliefs about the likely effect size before seeing the data.
Okay.
This prior affects the results. So let's say you expect there to be a large effect size.
Mm-hmm.
And that's your prior.
Mm-hmm.
But let's say the data shows that the effect size is small. The output, the result, will be from the Bayesian model that it's likely there is no effect. Because you expected a large effect.
Why would your initial expectation change
if you expected a small effect and your Bayesian prior reflected that, and the data showed a small effect, then the Bayes factor result would say, okay, there's likely an effect. Does that just at least conceptually make sense?
I think so.
Given the same data, your prior can have a very strong effect on the result of the Bayesian model.
Okay.
I know the whole concept of a prior sounds weird.
Yeah, intuitively it sounds like you'd be biasing it.
Yeah, I mean, it is a kind of way to think of it, and the Bayesian prior is always the problem with one of the main problems with the Bayesian modeling, that the way it's set up, you have to, just the way the math is set up, the probabilities, you have to determine a prior. Just okay, and so they are saying that we have chosen a moderately informative prior with this R scale value of 0.08. I'm being a bit quibbling with them because the Bayes factor documentation clearly states that a 0.08 R scale is not moderately informative. It's actually like outside of their range of default values. And that means this R scale of 0.8 is wider than ultra wide. It's not moderately informative. It's actually weakly informative. Sounds a bit counterintuitive, but this places more weight on the large effects. So it's a prior that says we expect a large effect from ApoB, for example, and pretty large.
Right.
And that means if you expect a really large effect and you only get a small effect, the result of the model will be probably there's no effect. because we thought
Right.
there'd be a really big one.
Is there a way for you to plug in the not actual, but like a more moderate prior, like the medium one?
Like
And would that be a good idea?
I'll actually, well, I mean, I can't, I don't have the data, but it's easy to do that. You just pick a different value and see what it gets. And this is.
I'm asking this a lot, but why would they do that?
I'll get to that. So
yeah, okay.
I just want to state this isn't a quote that they have. This is me explaining what the thinking is behind this. So it's saying, we believe ApoB has a strong effect on plaque progression within 1 year. However, if we don't observe strong effects in that time frame, we will treat that as evidence that ApoB likely has no effect because we expect large effects. So that's what they're saying with this choice of prior. It's not wrong. This choice of prior isn't wrong. I want to be clear. It's just the description is a bit misleading because they say it's conservative and moderately informative. Mm-hmm. And they don't explain well in the study how much of an effect it can have on the outcome.
Right.
Yeah. So normally you would run some sort of sensitivity analysis, which is, I think, what you were getting at, where you just look at how the results change with different prior values. So you would go through, like, what if we choose 0.2? What if we choose 0.3? Yeah. And that would be very simple to produce and very simple to show us. And these are just two quotes that, from the literature that says it's important to conduct a prior sensitivity analysis to fully understand the influence that the prior settings have on the posterior estimates. That's just the final results. And you can have strong opinion about the model parameter values, and this opinion via the prior can drive the final model estimates. Now, this is not the real data, of course. This is just what a sensitivity analysis could look like. So you have that R scale value from 0.1 to 1, and you would get these. This is that Bayes factor, that kind of semi p-value type thing. Mm-hmm. And let's just look at this column, the BF01. And their result was, in the ApoB model, was actually about 6.3 something. Mm-hmm. But what we see here is that when you change the prior scale, the R scale, it changes the result. It goes all the way from 1.8, which is like no evidence for this, to 12, which is like very high evidence for this. What we want to see is somewhere like a flatter spot, something that doesn't just go up, but something that like goes up and then like levels off and something like that. Because that would say that the prior has less of an effect on the result of the model.
Okay.
Does that make sense?
Somewhat.
Okay. Somewhat's good enough.
I think so.
All I'm saying is that the prior could have just affected the whole result.
Yeah.
And it's not clear
why they picked this.
Why they picked that. And it is also not clear that they picked that before they looked at the data. I don't know. They just didn't say anything.
Could they have started with something moderate, and then it didn't tell the result that they wanted to tell, and then they changed it?
Of course, theoretically, they could have. Ideally, you would set this up in the design and, within the construction of the experiment, you'd say, I've done an analysis on Bayesian prior, and because of this analysis, I've chosen this prior.
So we don't know.
No, we don't know. But that's what it is. Okay. So the last part about the Bayesian modeling is the Bayes factor interpretation. This is a direct quote from their study, and it says, in other words, these data suggest it is 6 to 10 times more likely that the hypothesis of no association between these variables, the null, is true as compared to the alternative. That is not what the Bayes factor says. The Bayes factor can only say that the data are 6 to 10 times more likely under the null model than the alternative. Not that the null hypothesis is 6 to 10 times more likely to be true.
Mm-hmm.
I know it's like a only statisticians would care.
What does that mean? Like, in so far as the results, how does that change the conclusion of their?
The conclusion isn't that the null hypothesis is more likely to be true. The conclusion is that the data shows that the data are 6 to 10 times more likely under the null hypothesis than the alternative. I know it's very simple. Okay. Basically, they like leapfrogged a big step in this conclusion. They would have had to state some prior odds, and then they could actually calculate the full posterior distribution, which then they could say actually the null is 6 to 10 times more likely. But they didn't do that, so they shouldn't say it in this way. I know it sounds like I'm splitting hairs, and I probably am. There are some things in statistics you shouldn't say, and this is one of them.
Well, the conclusion of their study was that there was no effect from ApoB on the plaque. Mm-hmm. What they're saying here is it's 6 to 10 times more likely that this was not by chance.
No, you're pulling in frequentist ideas. Don't think about p-value. That does have something to do with that, but I know where you're trying to get to, I think.
But it doesn't work with this.
No.
So how would they say? How would you say what I said, but from a Bayesian lens? What does 6 to 10 times? How does that connect with?
Then you would have to look at the result of the alternative as well and see, like, relatively what's the weight on each of them, and say you like in the end you can say the null hypothesis is 6 to 10 times more likely than the alternative hypothesis.
Okay.
There would be a kind of a way to also say a similar thing about the alternative, like the alternative hypothesis is whatever less likely than the null.
Mm-hmm.
I think you have to go back and learn a bit more about Bayesian modeling to be able to fully understand what they can say.
Yeah, I have questions about that, but none that wouldn't completely derail us into
yeah.
So
all this is to say that they overstated what the results were, and they shouldn't have done that. And I know it sounds like a little thing, but
they should not have done that.
I'm trying. Look, we're at the summary.
Whoa.
Okay. Just to summarize everything, we had the problem with having the change value as the outcome, so the change in NCPV, and they regress that on the baseline metrics, and that's widely discouraged in the statistical literature. It leads to the mathematical coupling, inflated error model on the model, and the interpretation of it clinically is not very useful, I think. It could be useful in some situations, but I don't think it's as useful as if you did it the way I was suggesting. And they had the conclusions of the study based on these univariable linear models. So only one predictor variable in the model. And there was no adjustment for other variables like age or blood pressure or anything. And that clearly leads to biased, unreliable, low credibility estimates for those betas, that slope and the significance of the models. Then they did Bayesian inference on top of that to support that there's no ApoB effect and that plaque begets plaque, but that's applied on top of these unadjusted and kind of structurally weak models, and it seems to just amplify these conclusions that I think is not a good use of Bayesian inference, let's say. And their prior scale, the choice of the Bayesian prior, I would say definitely would affect the output of the model, the Bayesian inference model. And we don't see any sensitivity analysis. So the results of that model are probably prior driven and not clearly stated why that prior was chosen and if it was chosen before the data was seen or things like that. Also, that little quibble before about the Bayes factor interpretation that they claimed that ApoB has that they said that ApoB has no association is 6 to 10 times more likely to be true, but that is a misstatement, an overstatement, saying that the Bayes factor is a posterior probability, but it's not. It just is comparing the model fit to the data fit to the model. It's not to truth. It's not that. You can't say that. I think they just misstated that. That's fair. And so I'll say their headline claim, their big plaque begets plaque, ApoB does not, isn't based on overstated evidence. It's undermined by methodological limitations, unadjusted modeling, and incomplete model reporting. And I guess also poor choice of outcome variable. That's my big summary. But wait.
I can see that there's like...
There's more.
Yeah.
Okay, I'll try to go through these quicker.
Okay.
All right. Okay.
Because I do have questions.
Yeah. Okay. So you had actually mentioned this before, that adjusting for multiple comparisons, like if you run 50 models, it's likely that you're going to get some positive result by chance. Yeah, they said nothing about adjusting this, and they did run at least 14 distinct linear regression models, maybe more, I don't know. But that increases the false positive risk. There are definitely ways to mitigate that. Basically, it's some way of reducing the p-value threshold, and no mention of that. That is generally okay if it's just an exploratory analysis, and you're just reporting it as like, here's what we saw in the data, here's some descriptions, these things are correlated, these aren't. But the way it was presented in the paper, like, it didn't come across as exploratory, I'll say.
Mm-hmm.
Okay. This is a bit technical, but okay, I'm going to explain this really simply. This zero inflation censoring and heteroscedasticity. Good word.
You made that word up.
I made
100%.
Okay, so NCPV at baseline. Many people had zero plaque in that plaque metric.
Mm-hmm.
Okay, now any measurement you do has error. Correct? Like,
Mm-hmm.
it's not, if you take the measurement 10 times on the same day, it's not going to be exactly the same. Correct?
Okay. I didn't know that.
Yeah. So the problem is if you're at zero, you cannot have an error, you cannot have negative plaque.
Right.
So any error that is associated with that zero value is a positive error.
Right.
And then if you have higher than zero plaque, the error should be symmetric around that,
Mm-hmm.
around what the true value. The problem is that this is a problem for modeling, basically, because it could produce residuals in the model that are not normally distributed, and it could also produce this thing called heteroscedasticity, which means that the variance becomes larger as the values increase.
Yeah.
So there are some assumptions about the data when you're doing linear regression.
Uh-huh.
And two of these assumptions are that the residuals should be normally distributed and that the variance should be constant. And if you invalidate those, then the modeling could be suspect, let's say. The results aren't like to be trusted.
Do you know for a fact that can plaque be zero?
Plaque can be zero, but it can't be negative.
And you know for a fact that some of it was zero? Because I wasn't sure if we had that data.
Yeah, you can see there's a chart, and you can see that there's a large mass of participants. There's a lot of participants that are at or very, very close to zero in the baseline measurement. And
the error thing, is that something that they addressed, or is it something that you're saying that could happen?
They said that, okay, so they said that in their modeling, it passed this check model function in R, but they didn't provide any output.
Okay.
And that's all I'm saying. Like, we don't know. There are methods to deal with this. You know, it's not like you can't do anything if that's the case. I'm just, because there's actually other similar studies that did find this was a problem in data about plaque. So it was just an issue that could be there, maybe not. I don't know. So I didn't put it in the main section. It would be cool to look at the data and see if it was an issue. Okay. Let's go. Okay. In this study, they do say that they performed a sensitivity analysis. So they say, this is a quote from the study, in the abstract, they say plaque progression predictors were assessed with linear regression and Bayes factors, diet adherence, and baseline cardiovascular disease risk sensitivity analyses were performed. Sensitivity analyses on this, the second quote is not in the abstract. The sensitivity analyses on participants with greater than 80% of beta-8 hydroxybutyrate measurements above 0.3 millimole per liter in those tables and with high calculated 10-year cardiovascular risks showed similar results to those just reported. Just reported means the main results we're talking about, like the no association between ApoB and those kind of things.
Okay.
This sensitivity analysis appears to have been done post hoc. That just means after the fact. And they did it in those two groups, the high adherence and the high CVD risk. So that's like high risk at heart disease. Those are just the numbers, 56 and that's part of the 100 group. But we don't know if this 28 is within this 56 or if that's a separate 28.
Okay.
That's not stated. So we don't know if that's like an distinct groups or if they're overlapping, because if they're distinct, it's more supportive of their data. Whereas if it's just, that group is within that group, it's not as confirmatory that you have two separate groups.
When you just presented it, I just assumed there's overlap.
Yeah, which is okay, but they didn't say that. Anyway, but they basically ran the same analysis on them. It's not like they changed how they came up with their results. So the same critiques of that. They say that the sensitivity analysis showed similar results to those just reported. That was the whole result of the sensitivity analysis. This is just pulling out. This table, the model just shows that regression model that we've been talking about. So the change in NCPV modeled by ApoB at baseline. They also did change in ApoB, which is kind of weird, but anyway, let's look at the bottom row. So this is the full, this column is the full 100. The second column is only that 56 with the high diet adherence. The third column, the right column is the high CVD risk. And if you just look at these Bayes factors, they are pretty different, actually. This Bayes factor is like very weak evidence for this model. For this model to be no effect. Sorry, this is the null that they're testing here.
Yeah.
I don't know. That is kind of interesting, actually. I would just want to know, is there something about the high adherence group that made it different? Like, this is more like, I want to look at that.
Isn't it kind of a moot point because they picked the prior...
But the result's still different. I'm just curious. It's just kind of... And the p-value is closer to 0.05. I don't know. I just want to look at the data. Anyway, that's about it on the sensitivity analysis.
I was wondering about
the number
sample size. Yeah.
Okay, maybe quickly. So initially the study's endpoint was just change in NCPV over 12 months, and it was not regarding modeling ApoB specifically. It was just looking at the change in plaque over 1 year. And this is, you can estimate how large a sample size you need for a study by what's called like a power analysis. And if you expect to get a small effect and you want to be able to detect that, you need a larger sample size. And generally this line here is that 80%. That's what you want generally, 80%. Don't think too hard about why it's 80. We'll just ignore that for a while for now. But if they only thought that they would get a small effect on ApoB in a year, they would need like 400 people to detect that.
Okay.
Statistically. However, if they thought they would get a medium or large effect, yes, they can get by with 100. That's fine. But we don't know, because that's not what this study was set up for. And as it says here, this is for one predictor in the model. If you have more than one predictor, you need more participants to get the same, to be able to detect the same effect size. That's to say, I don't know if it's enough. They've been saying, oh, it's probably enough anyway, but who knows? It's unclear.
That was one of the things I was going to say in the beginning of the problems that I thought might be. I thought 100 was way too few of people, but I wasn't sure.
Yeah. It probably is, but without a lot more research, I don't want to say for sure.
Okay.
But that's only for one predictor too. That that doesn't negate all those other issues.
Right.
All right. Okay. So after the study came out, it seemed like a lot of the authors were saying these lean mass hyperresponders are heterogeneous, and you have to treat them uniquely. Like, I don't know, there's a lot of variability in the plaque in the 100 subjects, even though they have similar metabolic characteristics, their plaque levels is very different. And so people were asking, like, why didn't you guys report an average change of NCPV in the study? Which they actually did not do. They didn't say the average change was this. They only reported these conclusions about ApoB and that plaque begets plaque. So people kept asking, and eventually one of the authors posted that this was the value of the change, the 18.8 millimeters cubed, whatever. But he said, like, if despite our results show that CVD risk among LMHRs, the lean mass hyperresponders, is heterogeneous, and thus a pooled summary isn't a good idea, you must have a numerical pooled NCPV change value. Here it is. This is it. This is just a bit strange, because they say the group is heterogeneous, which just means they're different. They're very different within the group on this plaque value. But on this group that's very different, that they don't want to report a pooled summary, they run all these regression models and base factor models on that group as like a pooled summary and report those models as a pooled summary.
Right.
And that's the conclusions. Like, what's the difference?
Right.
And if the group's too heterogeneous to just report like an average, like, then how can you report output from regression models?
Right.
And if the plaque progression isn't coherent or, at least somewhat predictive within this group, like, what's the point of this group?
Right.
I'm not sure, because everybody is heterogeneous in risk. Like, it's not like this group is special. Like, the same person with one ApoB value is not going to have exactly the same plaque as another person with the same ApoB value. Do you see what I mean?
Yeah.
Regardless of whether they're in this group or not. Like,
right.
So I don't know. It's just a bit strange line of arguing.
what kind of motives could they have?
I'm not sure if I want to speculate.
Okay.
Maybe we'll do that at the end. Stay tuned.
Some of the questions,
I know.
I mean, if somebody made it this far, I think.
Yeah, so they're going to see it. Yeah, we'll talk about that later. Okay. So usually in the scientific literature, you produce the study, it's published, and then other researchers like write letters to the editor like, why didn't you do this? Well, you should have done this, blah, blah, blah. And then the authors of the study respond in a letter, and the scientific journal publishes these. Okay. So there, just recently, a couple of weeks ago, I think, there was a letter to the editor published, and the response from the authors of the study was also published. I'm not going to read them. I'm just going to pull out some quotes just from the responses. Okay, this is from the response. So this is the study. This is the authors from the study saying this. Regarding the analytical points brought forward, we are aware of the relevance of linear assumptions to obtain accurate estimators, since residual plot evaluation can also be subjective. So you remember we were talking about the residual errors and the assumption that they should be normally distributed. So people were saying you didn't produce any output of the checking the model if the assumptions were valid, because they had similar questions to me, like, is the data skewed? Is it heteroscedastic? And the thing is, these residual plots, like, yes, that's one way of doing it, but there are clear quantitative tests that assess the model assumptions, like listed here. Like, just report them. Tell us what they are. Don't just say that the residual plot's subjective. Yes, the residual plot can be subjective, but there are other tests that are not subjective that you can do. And the function that they use will generate results of those as well, those more quantitative tests. They didn't say anything about those or give us the output, so I don't know why they didn't do that. And then following from that quote, so since residual plot evaluation can also be subjective, we followed their suggestion and reran all models with robust linear regression. As expected, there were small differences with the published estimates. All models using robust regression were consistent with what was reported. So that's that. No output, just similar. Okay. Great.
Okay.
Also in the letter, the response to the letter, they say, additionally, we'll highlight the mean change in NCPV was 31.5 millimeter cubed, with a standard deviation also of 31.5 millimeter cubed. This highlights the impressive degree of heterogeneity in NCPV change. So they're saying oh, we'll give you the pooled estimate that, they were talking about earlier. Now, this standard deviation, the same value as the mean, that's like really wide spread of values. And that's questionable. Like, that's a really high level of variation or heterogeneity. And that weakens all of the models. It makes them much more unstable in the results that they produce. Not just the null finding of ApoB, but all of the models. Like, it's just, if there's that much variation and your sample size is low, like, you should not make those strong conclusions. In the response, they also say, we completely agree our exploratory results, especially those suggesting a null association between plaque progression and ApoB, should be interpreted with caution. I don't think that was clearly stated in the study.
Right. Right.
Another another quote from that letter, that response. Moreover, our results are compatible with a causal role of ApoB in atherosclerosis, as we have openly acknowledged and supported in previous publications. So that is literally plaque in the arteries. So they're saying our results are compatible with ApoB causing plaque in the arteries.
Mm-hmm.
What?
Yeah.
I mean, I guess they're compatible in that statistically you're just saying it's an association. Because it is possible that you find an association, but that association is not a real association. But yeah, saying that they're compatible is...
Yeah.
Plaque begets plaque, ApoB does not. Yeah. More quote. Along the same lines, we would like to clarify that our title was not meant to be a statement about causality. Plaque begets plaque, which of course mirrors the proverb money begets money, is frequently used to highlight the strong and clinically relevant association of baseline plaque values with plaque progression rate. And then they cite a study that shows that as well. But in that study that I, of course, had to look at, they did perform what's called a t-test on the change scores, but their main conclusion in that study relied on a much more advanced model, which is called a random effects repeated measures multivariable regression model that modeled follow-up calcium score, that's like plaque, adjusted for baseline plaque and multiple other clinical risk factors. And that paper did not report any univariable linear regression models. And another quote from the follow-on quote from that. In retrospect, we might have chosen longitudinal data from the KETO-CTA study as an alternative phrasing to avoid misinterpretations for their title.
Mm-hmm.
And their title, Plaque Begets Plaque, ApoB Does Not. Misinterpretations.
Right.
Beget, definition, to cause.
I have a couple of things.
I'm sure you do.
They funded this. They crowdfunded this, and let's say the researchers were statistically challenged. First of all, is it common not to release the raw data?
Yes, that is common. It shouldn't be, but it is. Part of the reason is for privacy concerns. I mean, these are people's health metrics. Like, I understand that. Aren't
they anonymous?
Especially in this study, no, because the participants were recruited through social media, like Facebook groups from this, and maybe they'd be okay with it. I actually saw they said they might release the raw data further on, so we'll see. Hopefully they will. It would be really interesting to look at it.
My first question was, if they were to release the raw data, would that solve a lot of the criticism? And because people could just...
It wouldn't make any of my criticisms go away.
Sure.
Like,
but
I am not saying that their results are wrong. It could be that when they input more variables and they control for more factors, they will get the same results. That's possible. I don't know.
But we haven't done that.
None of it, if they did, none of it was reported.
Right.
So we just don't know. But that's not the point of the critique. The point of the critique is
but-
that their conclusions were based on these simple models, and
but if we're assuming that they're statistically challenged, that they had no idea how to do that.
I can't. I know at least some of the authors have done previous studies, and they weren't this statistically challenged.
I like that you tried to come up with a better term. It's good.
And these aren't like complicated. These aren't like concepts that you'd come across in like the advanced statistics courses.
Okay.
Like these are like,
pretty accessible.
Maybe not the first course, but like second, third, they'll start to come up.
Can AI do it?
Can AI do it? I would not trust AI to do it. No.
Okay. Not yet.
I mean, I don't know, maybe someday, but not now. And especially definitely not without checking everything very, very, very well.
Okay, here's one that you might not have seen coming. And it's I don't even know if you want to talk about this, but I'm gonna throw it at you anyway. You said this study was getting a lot of traction.
In those circles, yeah. Uh-huh.
As in circles of people who are interested in cholesterol and heart disease and things
low
like
carb
that.
people, maybe general nutrition health people, yeah.
Okay. So let's say somebody ended up on this episode of those people. Most of them aren't deeply interested in a statistics course.
Right.
But knowing what you know, because I'm assuming you have read a lot of different studies on cholesterol and heart disease.
Not all of them for sure, but yeah, I've read a lot of them.
I know this isn't your first.
No.
And I'm guessing some of the ones that you've read have been of higher quality.
Oh, for sure.
Okay, the conclusion that this study came up with, do you think it would hold up?
You mean if they did everything right statistically?
Yeah.
I think that, okay, this is, I want to just caveat this with, I don't know the data. I haven't seen it. This is just speculation at this point now. This isn't like, it's just based on my, background of doing a lot of data analysis and modeling. I think that they would confirm their findings that baseline plaque metrics predicted follow-up plaque metrics. But I think, I'm not clear what they would get from ApoB, but I think that was more due to the power, the number of participants and the time of follow-up, that the time's too short and that the number of participants are low and the variation in plaque is so high. I think that they're more likely to find a null result with that.
But isn't
which is exactly their conclusion.
I don't know how to say this other than like I'm super simplifying it, but isn't this kind of suggesting that eating a lot of meat doesn't increase heart disease?
That is definitely an interpretation of the study that has been promoted on some social media channels.
I think that's why this study has gained traction. Correct me if I'm wrong.
Yes, I would agree with that. That's most of it. Also, it was, there was this crowdfunding thing where people were invested in this and wanted to see the results because they, you're eating a low carb, high fat diet, and the general consensus says you're probably going to have heart disease in the future. If there's a study that says that, wait, that's probably not going to happen because we've taken this group who are otherwise healthy, except their cholesterol's high, and it doesn't find an association with plaque and ApoB, yay!
Right.
Which I get it. That's, that is it's people's lives. Like, that's why people get really emotional about this. But it's also why you should do the statistics right and be really careful about how you interpret the results.
Yeah. I mean, assuming that most people are actually, after finding out about the diet, like with good intentions, then they have a pretty good basis on how to do that now.
Yeah. Maybe I can step back out of the analyzing it in a statistical way a bit.
Yeah.
In my view, you cannot make any conclusions from this study. It doesn't give me any evidence one way or the other. I just don't see any way that you can look at the data and look at the results and have any confidence in these conclusions.
If you had the raw data?
Even then. It's 100 people in 1 year.
No matter what the results, no matter what the numbers say.
But I know at least overall what they say.
Yeah. Okay.
And it's if it had showed that almost nobody increased in plaque, that the mean change was almost zero, and there wasn't much variability in the plaque of these people. Yeah, that's something for sure. But it showed on average, and almost everybody increased their plaque volume. And whether or not it was due to ApoB or whatever, I don't think you can determine that from this study anyway, but it doesn't matter. It's not like this ketogenic diet saves you.
Right.
It definitely doesn't do that.
Okay. I think that's what I was getting at.
Yeah. There's one more thing I want to say. So we went over the choice of the outcome variable, that change in NCPV, and the problems with that. And I was looking at the other study that they mentioned in the letter, and in their final model, they got an R squared of 0.97. And if I'll remind you, 1 is perfect correlation. 1 is the model explains everything, basically. Yeah. Like, it's perfect. Yeah. 0.97 is crazy. And like, if I've done a lot of modeling, if I saw that value, I'd be like, I messed up something. There's something wrong. There's got to be some method I screwed up, or I somehow input the data wrong or something. Like, I would go back and figure out. And I was thinking, like, how could they get such a high correlation? And it's obvious. It's been on the tip of my tongue. This is just autocorrelation.
What does that mean?
That just means that the initial value is always going to be correlated with the next value.
Isn't that part of what you talked about in part 2?
Yeah, but this is a spin on it. Like, so this is like a time series modeling concept with this, like, think of the like the stock market.
Yeah.
There are tons of models that only look at the previous points of the values of the, like, the S&P.
Yeah.
So the highest predictor of the next value is the previous value.
Naturally.
Right. But it's not causal. It's not saying that causes that.
Right.
It's just like numbers, because a similar number will probably follow the previous number.
Yeah.
This is the same thing. Imagine if you had a plaque value every single day. It's like a time series.
Yeah.
And it's just autocorrelated with itself. And I know that this one, it doesn't sound as like interesting maybe to you. It just made me think of it in a different way, of, instead of modeling one point, like, this is just, it's just correlated with itself.
Yeah, because the outcome that they measured is literally
based on the previous value. And
no, that makes sense.
If they say plaque begets plaque, like, there's some sort of nonlinear growth. Like, say, for some reason, when you have this amount of plaque and then you get more, it increases non-linearly. Does that make sense?
Mm-hmm.
But that would be, I'm not sure if that makes sense biologically. Maybe it could, but it would be really interesting to try and figure that out. And maybe there's something to that, but I don't think that explains much of the outcome. Like, I think it's almost all of it is just that it's an autocorrelation. Correlating with the self, basically. Yeah. Maybe there's like a tiny percent that's like a bit extra because you have more plaque, you get more and more, I don't know. But, and I like, that's got to be the reason why they're getting these R squared values so high.
Yeah, that makes sense.
Yeah.
Yeah.
It'd be fun to get the data and look at it.
Maybe they release it.
I'll definitely do a follow-up then.
Yeah. I'm curious.
Yeah.
But I am also convinced it's what you said. It's just correlated with itself.
Yeah, and that doesn't mean it's causative. That's the weird thing. I don't know why they jump to causation. Not that they're saying that specifically, but that's the implication,
implied,
you know? Like, but how do you remove those effects and then see if it's, the rest of it's due to ApoB or LDLC or whatever, That's the important thing.